Está. Okay. Let's get started. Let's get started with a question just about power series. Let's say that I want to compute the following power series. Okay? Sum from k equals 0 to infinity of x to the k. Okay? You guys know what that is. This is a geometric series. And this is 1 over 1 minus x. Okay? Let me make a quick comment about this again with regards to what it means to what this equality means for us. Okay? If you're an analyst, maybe you would say, okay, this is true if the norm of x is less than or equal to 1. Right? It's less strictly than 1. That's what this converges when x is less than 1 in absolute value, or a norm if it's complex. Okay. As formal power series, remember we don't care about convergence. We just care about these algebraic expressions. So what does this mean algebraically? What this means is that when you multiply this series by the series 1 minus x, you get 1. So imagine you do 1 plus x squared plus x cubed, etc. You multiply them by 1 minus x formally as algebraic things, and what you're going to find is that you get 1. Okay. So that's what this equality means for us as formal power series. How do we compute this one?
But I have a question. When you get in calculus, when you get that demonstration of that geometric series, there is one term on top that is like a telescopic because you prove like the partials. Why would that term disappear?
So maybe what I will do is I think this is a good thing for you to compute for yourselves, and we can discuss it in the forum. You should really take this thing and multiply it by 1 minus x. Just carry it out and you will see that every term is equal to 0 except for the initial term, which is 1. I could explain it to you, but I think you will understand it better when we do the computation and you will see what happens. Okay, so how do I compute this one? Well, there's a couple of ways. There's one trick, which is what? We could take the derivative of this. What happens if you take the derivative of this? Well, the derivative of x to the k is k x to the k minus 1. When I take the derivative. What is the derivative of 1 over 1 minus x? It's 1 over 1 minus x squared. Okay. Okay, well that's not what I wanted. I wanted k x to the k. But I wanted k x to the k, but right now I have k x to the k minus 1. So in order to get k x to the k, I will just multiply this by x. And if I multiply by x, I get this. So I get x over this. And I can keep using this trick. So if I want the next one, I can take the derivative. Okay, so what did I do? I took the derivative and I multiplied by x. And so I could take the derivative of this and I'm going to get k squared x to the k minus 1. And then if I multiply by x, I'm going to get this answer. And if you do that, you're going to find that this is 1 plus x over 1 minus x cubed. It takes a couple of steps, but you can do it. And you can keep doing this indefinitely. You can do this for any fixed exponent. I'll tell you what the next one is. You get 1 plus 4x plus x squared over 1 minus x to the 4th. I can tell you what the next one is. It's 1 plus 11x plus 11x squared plus x cubed over 1 minus x to the 5th, and so on. Okay? Maybe you're surprised that my memory is so good that I can write these things down by memory, but actually my memory is not so good. It's just that these things have very nice properties. Okay? And so what I'm going to do is that I'm going to define.
It is like a Pascal triangle.
It's kind of similar to a Pascal's triangle, right? It's not exactly the same thing, but it's pretty similar. And one thing that is not difficult to prove is that you're always going to get some polynomial divided by 1 minus, let's do this for n. A(n), some polynomial divided by 1 minus x to the, what, n plus 1. Okay. This is always true. And this is very easy to prove by induction, and actually, I mean, we're basically giving a proof here, right? The proof, okay, well, the statement is that this is a polynomial. It's a polynomial of what degree? I guess it's of degree n minus 1. Okay? But you see that there's some properties. For example, there's a symmetric property. Okay? So that's one thing that actually it's also easy to prove. We will prove it. What else do you notice about these things? These polynomials? Well, when you look at them, I'll tell you what these are called. These are called Eulerian polynomials. So Euler knew how to compute these things. What do you notice? Do you notice anything about these polynomials other than the fact that they're symmetric? So let me point out one thing that happens. What happens when you plug in x equals 1 into the numerator? Here you get 1. Here you get 1. Or in other words, what's the sum of the coefficients? 1 plus 1 is 2. 1 plus 4 plus 1 is 6. 1 plus 11 plus 11 plus 1 is 24. So you see 1, 1, 2, 6, 24. Those are the factorials. Okay? And that's why it's very easy for me to do this in front of you, because I remember that it starts with a 1, I remember that it's symmetric, and I remember that it's supposed to add to a factorial. So this is a polynomial of degree n minus 1, and a(n) of 1 is what factorial? N factorial. Okay. And so this is what this is. Euler discovered this, and he found a recursive way of computing these polynomials. And actually, if I give you some time, you would be able to write a recurrence for these polynomials using this method. But this is something that happens very often in combinatorics. We have these polynomials, maybe they come from somewhere else, and we find that they seem to have combinatorial structure. Here you see the symmetry, and you see that the sum of the coefficients is n factorial. And so the natural question that a combinatorialist asks in this situation is, okay, there's 24 permutations of 4. So how do I group them into something how do I find a statistic? So that there are 1 permutations of statistic 0, 11 of statistic 1, 11 of statistic 2, and 1 of statistic 3. And so that's our goal here, is to find a statistic on permutations. And maybe, because we don't know where it's going to be, let me just call it stat of pi, such that if I do sum over the permutations in Sn, and I do x to the statistic, I get my Eulerian polynomial. Okay? This is something very typical in combinatorics, and you see, I mean, we all have our obsessions. And what is the obsession of combinatorialists? If we see a positive integer, we want it to count something. And so if I see an 11, I say, okay, well, there's 11 of what? 11 permutations such that something. Different things. If it's a topologist sees an integer, and they want to say that it's the dimension of the homology of something. An algebraist sees an integer and says, okay, you know what? This is the dimension of some vector space. We like it to be counting something. So that's what one of our goals for today is to discuss the answer to this question, which is actually very nice. And so what I'm going to do is I'm going to introduce another very natural statistic on permutations. is descents. Okay. So what are descents? A descent of my permutation W it's what it sounds like. It's when it descends, right? So is an I such that Wi is bigger than Wi plus 1. Okay, when the permutation goes down. So if I want the descents of a permutation like 1, 5, 2, 8, 4, 3, 6, 7, then I just need to say when it goes down, right? So from here to here I go up, from here to here I go down. So this is the descent. Here I go up, here I go down, from 8 to 4. Here I go down again from 4 to 3. From 3 to 6 I go up, from 6 to 7 I go up. So the descents are 2, 4, and 5. Okay. And the descent of,
It's not 4 by 8.
give me just a second. So with lowercase, this is just going to be the number of descents, which is 3. Okay. So the question is, why is it not 4, 5, 8? Because the descents are the positions, not the numbers. So second position, fourth position, fifth position. Okay, so that maybe it's useful to say a position I such that Wi is bigger than Wi plus 1. And you see here we're starting to get more comfortable with the different notations for permutations. Right? It will be a little bit easier to see it if I wrote it in two-line notation. If I had 1, 2, 3, 4, 5, 6, 7, 8, then you would see the 2 here, the 4 here, the 5 here. But here I'm just writing one-line notation, and so that's what it is. Okay. Okay, so maybe let's do for n equals 3. Let's do all the cases. So 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Okay. Let me give you another tip. So here I listed all the permutations. Whenever you're listing some combinatorial objects, it's good to do it in some order to make sure that you didn't forget anything. And so what I did here is that I listed them in alphabetical order. If you look at the permutations in the dictionary, this would be the first one, A, B, C, A, C, B. If I list them in alphabetical order, then I am more likely to get a complete list and not miss anything. So this is the permutations, and let's see how many descents they have. Okay? Maybe I'll use a different color. So what descent do I have here? Nothing. Right? Here it just goes up. Here it goes down from 3 to 2. Here it goes down from 2 to 1. Here 2, 3, 1, so it goes down here. 3, 1, 2, it goes down here. And 3, 2, 1, it goes down here and here. So the descents are 0, 1, 1, 1, 1, 2. Okay? And the point of what I'm doing here is that I have one permutation with 0 descents, 4 with 1 descent, and 1 with 2 descents. And this is precisely the coefficients of the third Eulerian polynomial. So that's what we're going to prove. So let's define A of nk to be the number of permutations of n with k descents. Okay? And so the theorem is that an of x, actually it's not, it's a little bit strange, but what I want is to do it with k minus 1 descents. And so the theorem is that an of x is the sum from k equals 1 to n of a of nk next to the okay, maybe a. I think I wrote this down incorrectly. Let me write this down and then help me fix it. So is this formula correct? what happens when k is equal to 1? Then I have a of n1 is the number of permutations with 0 descents. And I want it to be x to the 0, so I guess I should put x to the k minus 1. Okay. Or in other words, sum over permutations of x to the I had written this down, but now I'm wondering if I wrote. Oh, okay.
But you should have a 1, so you should have.
I think I used a different notation here in my notebook and over there. And so maybe, okay, so now I don't need this one. Okay, so that I have, this is 0 descents, 1 descent, 2 descents. Okay. So let me just warn you that in my notes, I define this to be a little bit different. I define the Eulerian polynomial to have an extra factor of x. So that's why it's a little bit off. So in my notes I wrote that the Eulerian polynomial was x plus 4x squared plus x cubed. That's why I have that shift of 1. But this is not too important, of course. Okay. So that's what we're gonna aim to prove. And again, there's many different proofs that you can give of a statement like this. But there's one there's one that's maybe the easiest, and that we've done over and over again. So for all the different statistics, what did we do at this point? We defined a statistic, and what was the next step? We had we found a recurrence relation. Right? So we said, okay, how do I compute this number in terms of smaller numbers, usually the numbers for n minus 1. Okay? And so I'm going to write down a formula that, again, is going to be very similar to other formulas that we've seen. This plus n plus 1 minus k times a of n minus 1 k minus 1. Okay? So that's it. How do you think the proof goes?
By integrating.
You're right for something we're going to do later. But remember that the way we're defining these numbers is to be the combinatorial things. Right? So far we don't know that this has anything to do with the problem of the series. We know that this is the number of permutations of n with k descents. But later we're going to do what you're suggesting. Any other ideas? Are you just being shy? What do we do? Even if you don't see the proof right away, what's the strategy that we use in this situation?
Take a permutation and look at the first element.
What we keep doing in these situations is take one of the permutations, right? It has length n, and if you want to reduce to the case n minus 1, just see what happens with the number n. Right? We keep doing that. We start with a permutation, and then throw out the number n, and see what happens. So that's what we're going to do. So proof. Consider the following function what I do is that I take a permutation. Let's say n is over here. And what I do is that I just delete the number n. Actually, this should be n minus 1. Because because I have one n, and then I have n minus 1 W's. Okay? So I take my permutation and I drop the number n. Okay? And what's the idea? The idea is that if this permutation has k descents, then how many does this guy have? I didn't change it so much, and descents are very local, and so probably the number of descents is pretty similar. Actually, what is it? How does the number of descents change here? Well, where can I lose or win a descent? Well, the descents over here are the same as the descents over here. If I have a descent here, I still have it there. If the descents over here are also the same as the descents over here. The only place where it can change is around n. Either here or here. So, how can I lose a descent here? Well, the thing is, or how can I gain a descent? But you see, the thing is that from here to here, I don't have a descent because n is the biggest guy, right? So here,
Wi is bigger than Wi plus 1.
exactly. So here, I have no descent, and here I have one descent. Yeah, so, I mean, let's say that I have A descents here and B descents here. So then I'm going to have A descents here and B descents here. And now, how many descents do I have here? I have exactly one. Right? Because from here to here I go up, from here to here I go down. So I have one descent. And how many descents do I have here? It depends. It depends whether Wi is bigger or smaller than Wi plus 1. So here I have 0 if Wi is less than Wi plus 1. And I have one descent if Wi is bigger than Wi plus 1. Okay? So what does that mean? Well, that means that if this guy has k descents, then this guy has k minus 1 descents in this case, and it has k descents in this case. And then you can kind of see how the proof is going to go. Because I have the case of k minus 1 here, and the case of k here. So presumably what happens is that in this case, I get this term, and in this case, I get that term. And so again, how does this go? Well, for example, to get this case, what we usually do is we say, okay, well, we had a map from here to here. Okay. Now let's say that we're in this situation, and let's see if I had, or maybe the other one is a little bit easier. So let's do the other one. We're going to do this a little bit quickly because we've done similar proofs before, so maybe I will just give you a kind of a sketch of the proof and I will let you finish. Let's say that we're in this situation, right? So every permutation here maps to a permutation here, but now the question is, if I have a permutation in this case, how many pre-images does it have under this map? No, sorry, I didn't mean to do this case. It doesn't matter too much, of course. To do the proof, you have to do both cases. But this one is a little bit easier to say. So this guy has k descents, this guy has k descents, right? And so now, if I'm in this situation and I have a permutation like this, and this permutation in total has k descents, then how do I get this one? Well, I need to put the n back. Right? Now, where can I put the n back so that this guy does have k descents? I need to put it at a descent, right? That's precisely the point. I need to put it where Wi is bigger than Wi plus 1. If this is the descent, then I can put the n in the middle, and that's going to give me a pre-image here. And so for any permutation in this case, there are k permutations that map to it, which is what explains this factor of k. For each one of these permutations, I have k pre-images. And in the other case, for each one of these permutations, I have n plus 1 minus k pre-images, which is basically the non-descents. And so, okay, this is a little bit of hand-waving, but I hope you see how the proof goes. And again, it's very important that you know how to write a proof like this, which is why I don't write all the details down, and I encourage you to fill in the details completely. And in the notes I do the proof completely, so you should look at it. Okay? But this is the end of the proof, basically. Okay? And again, this gives me a kind of a Pascal triangle-like way of computing these things. Okay? And then, having done this, then I can prove my theorem over here.
I don't see very well the symmetry. Why does the symmetry happens? Like on this proposition?
So your question is, given this symmetry, why is the result that the polynomials are symmetric?
Yes.
It's a little bit, yeah, it's not entirely obvious. If you look at this, okay, so the observation that he's making, and it's worth writing it down. Let's see, where should I write it down? Let's write it down. I have to plan very carefully because of the camera. But let's write it down over here. So here's the proposition. A of n k equals A of n, what? N minus, is it n minus k or n minus 1 minus k? N minus 1 minus k. This is the symmetry of those polynomials. Okay. How do I prove this? Well, it's not entirely obvious from here. But again, you know, given that the statement is so simple, maybe you don't want to prove it like this. You want to give a nicer proof. You want to say, okay, well, this is a permutation of n with k descents. This is a permutation. These are the permutations of n with n minus 1 minus k descents. And so what you need to do is find a bijection between these permutations and these permutations. And actually, that's a nice exercise that I have planned. Again, something nice for the forum is to give a bijective proof. It's not hard, but it's very useful. Okay, and then having done that, it's actually quite easy to prove this result. So the theorem that the Eulerian polynomials are given by these permutation numbers. Why is that easy? Because so let's give a little proof here. Again, we've done similar proofs, so I'm only going to give you a sketch. So we do induction. So if you already proved that sum of k to the n minus 1 x to the k over k equals 0 to infinity is the sum of a n minus 1 k x to the k minus 1 over 1 minus x to the k. Then how do I prove the next one? Well, we actually do the same trick that we already did. Right? We can just take this thing and take x times the derivative. So what we get here is the sum from k equals 0 to infinity plus k to the n x to the k. And then we just need to do that here. Okay? Okay, this is not so much fun, but you can do it. This is a quotient, so you know how to take the derivative of a quotient. You carry it out, and you find that you get exactly this. You find that you get exactly the right-hand side of that, which is equal to the left-hand side. So blah, 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 blah. So we get a recursive proof. We get an inductive proof of this result. Again, you know, there's many different proofs, and it's possible to give more direct proofs, and we will do that later on in the class. But at least now we have a proof that this is really the case. So those are descents. So we enumerated permutations by descents, and we get that it's these things. And actually, for that reason, these numbers are called Eulerian numbers. There's too many things in mathematics called Eulerian something because Euler did too many things. So these are the Eulerian numbers. There's something else in combinatorics that's called the Euler numbers, which we will discuss later. There's also the Euler number, which is E. So don't get those mixed up. These are Eulerian numbers in plural. Since this sequence A of nk. Okay. So, having done this, what's another thing that we can do? I want to remind you of a trick that we used last time. So last time we defined this thing that we called, I forget what we called it, maybe the fundamental transformation, that takes a permutation in cycle notation and then just erases the parentheses. And we showed how that goes from number of cycles to records. So we showed that cycles and records were equidistributed. And I told you that often you can take one theorem and through the transformation get another theorem for free. And so that's what I want to do here now. So recall that we have our fundamental transformation hat, which does what? Well, let's start with this guy since we already did it. Okay? And I call it W hat because remember that the hat goes from cycle notation to one-line notation. So because this is one-line notation, I call it W hat, and it comes from W. And do you remember how to get W? Remember what we did is we went left to right and we took the records. So what are the records? They're the biggest thing so far. So here, I guess 1 is a record, 5 is a record, 2 is lower, 8 is a record, and then these guys are lower. And so what is W? Remember what I do is that I start a new cycle at each record.
Isn't that different from one-line notation? Because one-line notation means that one goes to... Okay.
It's a bit confusing with all these different notations, so don't be shy about asking me things like this. But yeah, so remember, here I'm thinking of my permutation as a word. And I just look at what are the records of that, the kind of partial records of that word. 1, 5, and 8. And then for the inverse of this hat transformation, I just do this thing of opening a new cycle, and it's one of these guys. Okay? And maybe I'll underline them to remind you that this has the property that in each cycle, the biggest number goes first, right? And also, these numbers increase 1, 5, and 8. So this is in standard notation. Okay?
But I have a question about line notation. You say line notation means that 1 goes to 1, 2 goes to 5, 3 goes to 2, but there 3 doesn't go to 2.
That's right. So, I mean, and this is a very strange transformation because this is one notation, this is another one. So here, this does mean 1 goes to 1, 2 goes to 5, 3 goes to 2, etc. And you're saying, where does 3 not go to 2 here? And the answer is it's a different permutation. Here 3 goes to 6. And it's strange because you read them differently. You're supposed to read them in one-line notation, this you're supposed to read in cycle notation. And they're different permutations, so you shouldn't expect to get the same thing. Okay? So, what's the point of doing this right now? The point is that if I already know how to count permutations by descents, maybe I can transfer that through this transformation to get a free theorem about some other statistic. And so the question is, if I have a descent here, and remember, descents go in one-line notation, so that's why I point to here. If I have a descent here, what does that become here? So what are the descents over here? Maybe it's worth, I'm going to use a different color for them. Well, Maybe I'll circle them, because colors are a little bit hard to see. So what are the descents here? This is the descent, 5 is bigger than 2, then I increase, then 8 is bigger than 4, 4 is bigger than 3, and then this is not a descent, this is not a descent. And let me remind you that this is meant to be descents. And this is meant to be, what did I say? Records. Okay. And then over here, these guys are the beginnings of the cycles. But the question is, what are the purple guys? What happens at 5, 8, and 4 that doesn't happen for the other guys?
They don't have a right parenthesis.
They don't have a right parenthesis, but it's even more than that, because these guys also don't have a right parenthesis. So you understand the question? The question is, what is different about the purple guys than the other guys in this permutation? And you should think that, I mean, just go by the definition, right? So what does it mean that 8 is a descent? Or it's not 8 that's a descent, right? It's so here 4 is a descent because the fourth number, w hat of 4, is bigger than w hat of 5. That's the reason that 4 is a descent. And so here, what I'm saying is, 8 is bigger than 4, right? So the fourth position is a descent because the number 8 is bigger than the number 4. So here the number 8 is bigger than the number 4. But what does that mean for this permutation? Well, in this permutation the rules are different. This is cycle notation, so the way that I'm supposed to read this is that 4 is W of 8.
Wouldn't be like pi of 8?
I'm sorry?
Well, W doesn't go from that to that, and wouldn't it be like pi of 8? Like the permutation?
Oh, so I'm calling it W, but it's the same thing as pi.
Okay.
So, because I call it W, then that means that W of 1 is 1, W of 5 is 2, W of 2 is 5, W of 8 is 4, etc. So you see, this 8 bigger than 4 says that 4 is a descent, and it says here that 8 is bigger than W of 8. Okay? Maybe let's do another one. So, here, 2 is a descent. It's very unfortunate that the 4 and the 4 get in the way here. So, maybe let's do this one. So here, the fifth position is a descent. Because why? Because 4 is bigger than 3. Right? In other words, W hat of 5 is bigger than W hat of 6. What about here? What does that say for this guy? 4 is bigger than 3. In the language of W, it says that 3 is W of 4, so it says that 4 is bigger than W of 4. Okay? So where I'm headed with this is that whenever you have a descent here, here you have an I such that W of I is less than I. And that's what's special about these circled numbers. They are the ones such that W of them is less than them. So let me write it. And these things are called non-exceedances. Wi is less than I. So you see, the W of 1 is not less than 1, so that guy doesn't count as a non-exceedance. W of 5 is 2, which is less than 5, so this guy is a non-exceedance. W of 2 is 5, which is bigger than 2, so that's not a non-exceedance. And so you see that the point is 5, 8, and 4 and are the non-exceedances of W. The number such that W of them is smaller than. And so this hat thing takes me from descents to non-exceedances. So that I have a bijection from Sn to Sn, which takes descents to exceedances. And therefore, because I know how to count permutations by descents, for free I get how to count them by non-exceedances. So the corollary that I get, budget my board here. The corollary that I get is that A of nk is also the number of permutations of n with this many non-exceedances. I forgot what, did I have k descents or did I have k minus 1 descents? Is it k minus 1? So then I should put k minus 1 here also. That's the corollary of what happens here. But actually, I could also, instead of counting non-exceedances, so okay, and I could count exceedances. So what's an exceedance? It's an I such that W of I exceeds I. That's why it's called an exceedance. So maybe this is more natural than that. Okay. So do you think I can replace non-exceedances by exceedances and get the same answer? Maybe it sounds reasonable. The number of times that a number is bigger, that W of I is bigger than I, it sounds kind of like the same thing as W of being less than I. It's kind of a symmetric thing. And so again, I encourage you to find a bijection that shows that actually non-exceedances are equidistributed with exceedances. They're more or less the same notion, I'm just changing from less than to bigger than. So that sounds like it should be the same thing. And let me give you another one. So what should a weak exceedance be? Well, it should be the same thing except that the inequality is weak. Okay. Now this is actually it's a little bit different from this. But it's also possible to prove that this is the number with k weak exceedances. And maybe it's worth actually doing this in an example so that it's concrete. So let's do it again. For n equals 3. Let's do W and then weak exceedances of W. So again, I list all the W's, 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. And I'm listing these in one line notation. Okay? So, what are the weak exceedances of 1, 2, and 3? So they're the positions such that W of I is greater than or equal to I. So here, what's W of 1? W of 1 is 1. W of 2 is 2, and W of 3 is 3. So they're all equalities here, so actually here they're all exceedances. What are the exceedances here? Is this number bigger than or equal to 1? Yes. Is this number bigger than or equal to 2? Yes. Is this one bigger than or equal to 3? No. So I get 2. Here, is this bigger than or equal to 1? Yes. Bigger than or equal to 2? No. Bigger than or equal to 3? Yes. Bigger than or equal to 1? Bigger than or equal to 2? No. So I get 2. Bigger than or equal to 1? Bigger than or equal to 2? No. Bigger than or equal to 3? No. And here, bigger than or equal to 1? Yes. To 2? Yes. To 3? No. So I get 2. And so you see that it's the same distribution as before. I have 1 of this kind, 4 of this kind, and 1 of this kind. This is this Eulerian distribution. So at least this is, it's very small evidence, but it's some evidence for this. And again, it's possible to get bijections between these things, and it's not very hard. I just wanted to show you one of them, which is that one, and then you can derive the other ones through some tricks. I mean, maybe it's worth discussing. How do you go from a permutation with a certain number of exceedances to a permutation with where the exceedances become non-exceedances? Huh?
You could just flip it over so that if pi of n was k, then pi prime of k would be n.
Right. So, and what is that transformation called? It's just the inverse permutation. So, yeah, so, I mean, maybe, because I proved this for non-exceedances, and I've stated here for exceedances, for example, let's give a bijective proof from here to here. And the bijective proof goes like this. It says, okay, now I use a different bijection from Sn to Sn, not the half bijection, but the bijection from Sn to Sn, which takes W into the inverse permutation. So if W of A is B, then W inverse of B is A. Okay. And so the claim is that the number of exceedances of W is equal to the number of exceedances of non-exceedances of W inverse. Why? Because I is an exceedance of W if and only if, well, what does it mean to be an exceedance? It means that W of I is bigger than I. Okay? But let me rewrite this as W of I is bigger than W inverse of W of I. This is the inverse permutation, so W inverse of W is the identity. And what is this saying? This is saying that W inverse of this thing is less than it. In other words, it's saying that W of I is a non-exceedance of and so then this is a bijection between the exceedances of W and the non-exceedances of W inverse. So this is how you prove that exceedances and non-exceedances are equidistributed. So you see, I mean, the possibilities here are endless. There's so many different transformations from permutations to themselves, and you can use them to transfer results from one place to another. Okay? Any questions about that? So, well, let's erase all of this and let's. So now I want to introduce yet another statistic. So the statistic is called the major index. And the reason for the name is kind of silly. Actually, it's called the major index because the person who invented this was a major in the army in England, I think. That's why it's called major index. So the name is not very enlightening. The major index of W is what I do is that, and maybe we can go back to the other permutation that we had, 1, 5, 2, 8, 4, 3, 6, 7. What I do is that I look at all the descents of my permutation. Okay. So what were the descents here? This is a descent, 5 to 2. This is a descent from 8 to 4, and this is a descent from 4 to 3. So the descents we said are 2, 4, and 5. This is descents. And what I do is that I just sum these numbers. Okay. So 2 plus 4 plus 5 is 11. Okay, that's called the major index of this permutation. It seems like a strange thing to do. How big can the major index be? What's the biggest that the major index could be?
The sum of I over ON.
So this would be the biggest if everybody is a descent.
And the square plus N over 2.
And so that's 1 plus 2 plus 3 plus up to n minus 1, right? Because this guy, the last guy is never a descent. And so you get the numbers from 1 up to n minus 1. So it's n minus 1 times n over 2. Or n choose 2. Okay? So this major index goes between 0 and n choose 2. Do you remember another statistic that goes from 0 to n choose 2? I know we've seen so many different statistics, but for example, the descents went from 0 to n, right? How many times you go up or down. The number of cycles, well, you can have at most n cycles. But what is there that you can have n choose 2 of? Remember the inversions of a permutation are the pairs that are out of order. So inversions are pairs. And so inversions are something else that go from 0 to n choose 2. Okay? And so what I'm going to prove is that the major index and the inversions are equidistributed. And we'll do an example of this to remember what all of these things are. But again, what this means is that if I look at this guy, I'm going to get the same as if I do this by inversions. Okay. And this should sound very strange to you. What I'm saying is that the number of permutations that have k inversions, k pairs out of order, is equal to the number of permutations for which this weird sum is equal to k. And I'll remind you that we computed this. And we found that it was this number, this q factorial, right? 1 plus q, 1 plus q squared, to 1 plus q plus q to the n. So this is the result, and again, I think it's worth it to do this for n equals 3. So there's the permutations. I realize now that I keep switching between pi and w. So anyway, it's the same thing. So pi, then the inversions of pi, and the major index of pi. So that we can see this in action. Okay. So again, let me list all the permutations. And let's compute all of these things. Okay. So inversions. Let's do inversions first. So inversions, remember, are the pairs that are out of order. So how many pairs are out of order here? Well, everybody's in order here, so there are 0 inversions. How many pairs are out of order here? Only the 3 and the 2. Okay, so this is 1 inversion. Pairs out of order here, just the 2 and the 1. What about here? The 2 and the 1, and the 3 and the 1. But the 2 and the 3 are in the correct order. Here, the 3 and the 1, and the 3 and the 2. And here, every pair is out of order. 2 and 1 is out of order, 3 and 1, 3 and 2. Okay? So these are the inversions. Now let's do the major index. So what we do is again, we first figure out what the descents are. So here, this guy never descends. This guy descends here. This guy descends here, from 2 to 1. This guy descends here. This guy descends here. And this guy descends here and here. But what I'm supposed to do is not count the descents, but add the descents. Okay? So here, there's no descents, so they add up to 0. Here the descent is in position 2. Here it's in position 1. Here it's in position 2. Here it's in position 1. And here it's in positions 1 and 2. And so I'm supposed to add those two numbers and get 3. And so you see what the statement is saying is that these purple numbers are the same as these orange numbers. I have 1 0, 2 1s, 2 2s, and 3. Okay, so how do we prove something like this? Well, there's several different strategies. One strategy could be that, because we already computed that the inversions over here are given by this polynomial, then I could just prove that the major index is also given by this polynomial. But I'm going to try to give a bijective proof. Right? So I want to find a bijection from the permutations to the permutations, which sends the major index to the inversions. Okay? So is it clear what my strategy is? I want to give you a rule that given a permutation, I'm going to give you another permutation, and then the major index of this one equals the inversions of this one. Now, I hope you can appreciate that this is a much trickier thing than before, because the major index and the inversions sound completely different from each other. And so this permutation, this bijection is going to have to be more complicated. And I just want to show you what a complicated bijection looks like. Sometimes they're not so simple. Okay, so let's see, how should I do this? This is going to be, let's go over here. Okay, so theorem, okay, I should not erase that, but theorem, the sum of q to the inversions equals the sum of q to the major index. Okay, and so my goal is going to be, so my proof is going to be to construct from the symmetric group, or from the permutations to the permutations, such that the major index of W equals the number of inversions of V of W. Okay. And if I do that, then I will be done. And just to kind of see what I need to do here, I need a bijection from these permutations to these permutations that sends the purple numbers to the orange numbers. So what I would need to do is I would need to say, okay, well, I have to map 1, 2, 3. I'm going from major to inversion. So I'm going to have to map 1, 2, 3 to 1, 2, 3 because it's the only 0 and the only 0. I have to map 3 to 1 to 3 to 1. But then here it's not clear if I should map this permutation to this one or to this one. And whether I should map this one to this one or to this one. And you can imagine as it gets bigger, it's much harder. But so that's what I'm going to do. And it's going to be given by the following thing. Okay, so given W, and I'm going to consider W as a word, I'm going to define words gamma 1, gamma 2, up to gamma n recursive. The first word is just going to be the first letter. Okay? And struggling how to write this down in the board so it fits. But okay, so then once I have my ith word gamma I, I'm going to do the following thing. I'm going to do 3 steps. First, I'm going to split it. Let me just write down the rules real quickly, and it's very hard to understand them without an example. So then we'll do an example. So I'm going to say Wi is bigger than Wi plus 1, split after each number bigger than Wi plus 1. And if Wi is less than Wi plus 1, then I'm going to split after each number less than Wi. Okay? Okay, we'll do this in an example in a second. So then in the next step I'm going to rotate each resulting compartment one to the right, and I'm going to add Wi plus 1 at the end. To get gamma I plus 1. Okay? So this is some procedure to go from the word gamma I to the word gamma I plus 1. And then the point is that gamma n is going to be my phi of W. Okay, so you perform this procedure, and when you're done with it, the word that results at the end is going to be phi of W. Okay, now let's see what on earth this is supposed to mean. So let's do an example. W is 6, 8, 3, 9, 4, 1, 7, 2, 5. Okay? And so out of W, I'm going to build these words up, gamma 1, gamma 2, etc. Okay? So for example, okay, gamma 1 is very easy, as I said. In gamma 1, you just take W1, okay? The first number. and then I'm supposed to split it. Okay, so I'm going to make a little table here where I haven't split it, and here I have split it. Okay, but okay, and here I always compare wi to a wi plus 1 to decide whether to split or not to split. Okay? And so in this case, I need to compare 6 and 8, and I find that 6 is less than 8. But anyway, this is a boring case, and here I haven't, there's nothing to split yet. Okay? So we'll see what splitting means in a second. Okay? So I go, okay, I have gamma I split it, in this case there's nothing to split. I rotate, in this case there's nothing to rotate. And then I add wi plus 1. So I add the next number 8. And that's going to give me gamma. Okay? And then I'm going to say, okay, now I compare 8 and 3. 8 is bigger than 3. So then I'm supposed to take this permutation and split it. And where do I split it? I split it after each number bigger than 3, because I'm in this case. Okay, so I'm going to circle what I need to do. So I split after every number bigger than 3, which means I split here, and then here I don't need to split because that's the end of the permutation. So this is my splitting. Now I rotate each compartment. So the compartments are these pieces, but the idea is to rotate them by 1, but there's only one thing, so there's nothing to rotate. So again, it's still a little bit hard to see what's going on. In this case, there's nothing to do except to add the number 3 here. Okay? And then I do the same thing. I compare the 3 and the 9. 3 is less than 9. And so that now I hope my splitting is starting to become a little bit clearer. So I take the 6, the 8, and the 3, and I split after each number less than 9. 6 is less than 9, I split. 8 is less than 9, I split. And here I don't need to split because it's the end. Rotating is trivial, rotating is trivial. So let me go to the next one. I add the next number. 6, 8, 3, 9, and now starts to get a little bit more interesting. So now 9 is bigger than 4. Okay. And so what I need to do, I think I have a typo here. Sorry. It's 9 plus 1, but it's basically what I'm doing here. I think this is a lot clearer than this. Okay. 9 is bigger than 4. So I split after each number which is bigger than 4. So 6, 8, 3, 9. So who's bigger than 4? 6 is bigger than 4, 8 is bigger than 4, 3 is not, and then 9 is the end. Okay. And so here I actually start to rotate. So the 6, trivial, 8 is trivial, but what I mean by rotating is that I rotate this cycle around. So move the 3 1 to the right and move the 9 back over here. So I get 6, 8, 9, 3. 6, 8, 9, 3 because I rotated this slot, and then I add the next number. Continue. 4 bigger than 1. So here, everybody's bigger than 1, so I split everywhere. Okay, again, the rotating is trivial. So I get gamma 6 is 6, 8, 9, 3, 4, 1. Then in the next step, I compare 1 and 7. Okay. So now I split after the guys that are less than 7. So 6 is less than 7, 8 is not, 9 is not, 3 is less than 7, 4 is less than 7, and 1. Okay. Now the rotating is a little bit more interesting, so I get gamma 7 is the 6, then 8, 9, and 3 rotate 1 to the right, and so I get 3, 8, 9. And then 4, 1, and I add the last guy. So 7. Okay? So is it clear what I'm doing? And if Again, this is the kind of thing, it's a lot easier if you do it than if you watch me do it. So I encourage you to maybe do it yourself and then stop the video, do it and see if you get the same answer. You keep doing this until you're finished. Okay? And I'm a little bit short on time, so maybe I will just tell you that when I'm finished. Well, I'll just tell you what gamma 8 and gamma 9 are. 6, 3, 8, 9, 4, 7, 1, 2, and gamma 9 is 3, 6, 4, 8, 9, 1, 7, 2, 5. Okay? And so the end result of this bijection, very strange bijection, is that phi of W is this thing, 3, 6, 4, 8, 9, 1, 7, 2, 5. Okay? And my claim is that the major index of this guy is the number of inversions of this guy. And so I hope you see that this is no longer something you just see, oh yeah, obviously. You have to work to prove this, right?
How they came up with this idea?
I have no idea. I mean, these are the kinds of things when you discover it, okay, it goes through a long process and then when it's written it looks like magic. But clearly that somebody didn't just invent this out of nowhere, there must be a process to get to this. Let me explain a little bit about why this is the case, that the major index of this guy is the number of inversions of this guy. The thing is that, how does the, I'll say one word about this, and again there's a proof in the notes, but let me say one word about why this works. So the key fact is, what is the change in the number of inversions when I do this process? So for example, from here to here, how many new inversions do I have? None. From 0 to 0. From here to here, I have 6, 3 and 8, 3. So I have 2 new inversions. From here to here, I have none. So on. Actually, it's easier if I just write it up a little bit closer. So plus 0, plus 2, plus 0. And if you do it, you'll find that this is plus 4, plus 5, plus 0, plus 7, plus 0. This shouldn't be obvious, but it's true. And so you see, how do the inversions go up? They go up whenever you have a descent. Right? If I don't have a descent, plus 0. If I have a descent, plus 2. If I don't have a descent, plus 0. If I have a descent, plus 4. And so you see, every time that I have a new descent, the number of inversions changes by the descent. By 2, 4, 5, 7. And so that's why the total number of inversions is 2 plus 4 plus 5 plus 7, which is precisely 2 plus 4 plus 5 plus 7 are the descents of this guy. And so that's why you get the major index. And so the way that you come up with a bijection like this, I guess, is to kind of try to come up with a procedure like this, where you win inversions in the right way, and then if you think about it hard enough, I guess you come up with the right way, the right thing to do. Okay? So I wanted to show you this so that you are not led to believe that bijections are always very easy. Actually, one thing that's not clear at all here is why this is a bijection. And it's kind of tricky to prove that given this one you can recover the original one. So there's several things to prove. And again, you can read the proofs in the book. I just wanted to show you more or less what this looks like. And this concludes the discussion of statistics and permutations. Okay? And so, but again, maybe I want to take a minute to just step back a little bit and talk about what we did in the last couple of classes. I wanted to talk very concretely about permutations and just do lots of statistics so you see that you can take one combinatorial object and there's a lot of richness inside it. And so given any kind of combinatorial thing that you want to count, you can start asking, once you've finished counting that object, you can start asking finer questions. So that's the whole kind of business of finding statistics and permutations, which leads to a lot of very interesting combinatorics. So I think that's it for today. Yo creo que apaguemos la cámara y un par de cositas. Me pidieron que